Okay, welcome to Oceanography. This is week 5. We're continuing today with chapters 6 and 7. For those of you keeping up in the notes, the note PDF that I sent out with 3 slides per page in the notes section from last week, that's going to correspond to much of what we'll continue to discuss in today's lecture. So we'll be carrying on to the chapter 7 content of the in that PowerPoint PDF that I sent around. And so what I want to do today, we'll continue that lecture. Before I do that, I'm going to talk about the team homework. So I'm kind of going to do these items in reverse order. So we'll do a review of the homework assignment that was given out last week, the team homework assignment, and that was the water column structure assignment, where you were looking at different properties of salinity and temperature that seawater can exhibit, and trying to understand how these different properties produce a structuring of the water column, structuring stratification by density. And grasping these concepts is important, because we're going to start, after we understand how water is structured, we're going to start moving it around with physical and processes, winds, currents, etc. And then we're also going to start populating it eventually with animals that and plants that occupy different regions of the ocean. So understanding the way that the ocean is stratified, and the way that the stratification produces different distinct realms and how they interact is really important as we continue with our exploration of the function of the oceans. So I'm going to struggle a little bit with the screen capture here. So I'm going to stop sharing, and I have to reshare. And I'm going to go to course modules. Okay, share. So your homework, team homework for this that was due on Sunday, is in this PowerPoint, this page here. And this was asking you a whole series of questions, and a lot of it was based on this diagram. This is a diagram that I showed in lecture last Thursday, and discussed how these lines of density, these contours of density, and contours is something that comes back again and again, that these contours of density are created by different properties that can result from different properties of the ocean, the salinity and the temperature specifically. And so what I was asking you for was to consider the 2 water samples from this 1.028 isoplet of density. And so the question was, if you mix these 2 points together, what would the approximate salinity and temperature be of the resulting water? Well, I'm not going to do the arithmetic, but if you just take the average of this, which is about 35.1, and about salinity in about 4 for A, and then if you take the average of that with this looks like about 12.5 and about 37.3, something like that. If you average those 2 numbers, that'll get you the approximate salinity and temperature of the resulting water. What would the density of that water be? Well, it would be somewhere between 1.028 and 1.029, probably 1.0285 or 84, something like that. I accepted that. And what would the approximate sigma t would be? Well, you take that number and subtract 1,000 from it, and that gives you a value of about 28. And then what would happen to the mixed water after it forms? Well, we discussed that in class. That's going to sink. Okay, so any questions about this diagram and understanding how this diagram works? Now is the time to ask. Please make sure that you understand this and that you're able to grasp these concepts. So any questions about this, please? No questions. You've all got it. All right. And then you were supposed to go through and define these following terms. Well, when I'm asking you to define terms and these kinds of things, what I'm really encouraging you to do is to go into the index of the book or read through the chapter and find the different terms. These are all defined and discussed in the text. And so what I was asking you to do was to find those definitions, to read them, to reproduce them in your own words as a team, so that you had a firm grasp of what a calorie was, for example, or what the latent heat of evaporation, a polar molecule, and so forth. So I wouldn't expect that there'd be any questions about these definitions, but Carrie, you indicated that that there was some issues with the definitions in some of the team homeworks. Could you elaborate a little bit on that, please, Carrie?
Some of them were just a little incomplete, especially with 10, 11, and 12. You would say that there was a change, but not say what the change was, and things like that. I just could have provided a little more information on some of them.
Yeah, and that's the point. I mean, so, you know, there are 5 or 6 people on each team, so you can divide the assignments up amongst the different team members, and you're all going to get together and see what everybody else has done. But if you've only got a couple of these, you can spend time and fully develop the, whatever part it is. All right. So, if you're doing a definition, and if I'm asking you for a definition here in a homework, there's a non-zero chance that that same definition will show up on a midterm exam. Okay. All right. And so the next. Great. Go ahead. I heard a question. I guess I have an echo from somewhere. Okay. And then I asked you to go to this diagram and do the contours of this diagram. Well, let me try to do that. Show you how this works on the screen, make sure everybody's got the contouring question together. So I'm going to stop sharing here. And start sharing. Okay. So this is the set of readings that you were given and asked to contour. Now, so what do these different columns of numbers represent? Any ideas? Anybody want to say? I can start calling on folks. So if you want to raise your hand or let me know. So what do these individual columns of numbers represent?
Temperature.
Temperature, yes, but why are they arranged in columns? How would you get these columns of numbers? What do you think, Saj? Sage?
The temperature is at different depths of the ocean at the different stations.
Right, and how would you get that? How would you know that? Remember I talked about the CTD and the rosette? So each one of these points would be a place where the scientists or the technicians had stopped their ship and lowered one of those CTDs and rosettes over the side. And then these are the numbers that they got back from their lowering. All right. So this is a cast, what we call a CTD cast, meaning that you cast it over the side. And then each of these numbers are recorded for the depths and distance from shore. So this is the depth in meters. So this is every meter down to whatever the maximum depth was. Okay. And you remember that that's what that conductivity, temperature, density profiler did, is it gives you a profile of the ocean at a particular point. Okay, so once we've got that, let's see if I can get over here. The challenge was to go ahead and contour these lines in half-degree length. So let's just start right here. So I'm going to draw a contour here. So I'm going to go through 5, and I have to go down through this 5, and I have to keep going down through 12.5, and 12.5 is here. 12.5 is here. 12.5 goes across like this. Starts going up. Goes down a little bit, I guess. It's up and there. Okay, so there's the 12.5 contour, right? Everybody should be able to do that. What's the next value on this? 12.0. So I'm going to go 12.0. Okay, is this kind of what everybody did? Next one would be 11.5. 11.5, 11 point, so that goes like in there, and I'm not gonna, it's probably like this, I guess. Across here, hand is shaking a little bit. Okay, next one would be 11. Something like that. The next one would be 10.5. Well, 10.5 doesn't show up here, but here it is. Here's 10.5. And I'm not going to spend a lot of time on this, but this is kind of how this is going. 10.5, 10.5, something like that. And then 10. So it goes like this. 10, 10, 10. And we don't have 9. I guess at the very bottom we have 9.5. So here's 9.5. Something like this. It's up there. And then 9 is at the very bottom. And on the top, we go from 12.5 to 13. So that's 13. And then 13.5. And 14 is just a little scrap of 14 somewhere in here. Okay, so that's what you should have ended up with, something like that. Is that what everybody got? Carrie, what did you think? Did everybody get this, or were there variations like on this, more neatly drawn?
A lot of people did things similar to this. Others created separate graphs. So I think some people just misunderstood what you were wanting them to do.
Okay, so when I talk about contouring and what we're talking about contouring, what we're indicating is that, that a contour is always sort of lines of some constant value. And this is when we're dealing with temperatures in the water, for example, these contours, the gradients can be very, very gradual. And when we look at the physical properties of the ocean, we're going to find that, for example, the height of the ocean, sea level, varies by a meter or two across ocean basins. And so that's a very subtle variation. You would never, if you had a large area of the Earth as large as an ocean, and there was only a meter or so variation in height of that surface, you would never, you wouldn't perceive that, you wouldn't be able to see that. But when we're dealing with properties like temperature and salinity, we can measure those, and we can determine that they follow specific structural rules. And so that gives us important information. It's the same thing with air pressure, air temperature, and so forth. We can contour variables down to very fine gradients. Okay, so what do we see in this sheet? So that's how we're supposed to do the contouring. And then for the homework, we were meant to answer some questions. And so what were the questions? Contour the isobaths. What is the slope of the bottom between stations 1 and 4? Well, how do we know the depth of the bottom stations in 1 and 4? Well, here's station 1 and here's station 4. Where's the bottom? So here's the bottom, right here. So the depth of the bottom at station 1, 10 kilometers offshore, is 10.7 meters. And station 4, which is 16 kilometers offshore, is only about a meter deeper. Okay? So what we would want to know is, I'm going to give you a little hint here, what's the change in depth over distance? So the change is, in this case,
You were looking at the temperatures, not the depth.
was I looking at temperature?
Yeah, it's about an 8-meter depth difference.
Oh, 8-meter depth. I'm sorry. Yes, thank you, Carrie. Not letting me draw here. Oh, because it's zoom. Well, so that would be 8 over 4, 8 meters over 4 kilometers. And so if you looked at the slope, let's see, 1, 2, 1, 4, that would be the arctangent of 1/2 of 2, right? We probably should do it in meters. So 4,000 meters.
And this is 6,000 meter change in distance.
6,000 meter change in distance. Okay. So 8 meters. Let me bring up a calculator. Let's see. No. So the slope here works out, if you take the arctangent of 6 over 8 over 6,000, works out to about 0.076 degrees. So it's a very, very gradual slope, okay, relatively flat. All right. How far offshore is the warmest surface water? Well, the warmest surface water is at about 14.3 degrees. So the distance offshore would be 26 kilometers here. And do you see evidence for a thermocline in this profile? Okay. So do we see any abrupt changes in this? There really isn't. Everything is going down pretty gradually. So we haven't reached the depth of the thermocline in this diagram. Okay, so that's a review of the homework. And I know I've gone over this and it's a little hard to present all these things over Zoom, but hopefully you get an idea of how this is supposed to work. Are there questions about the homework, the team homework?
I have a question.
Yeah, go ahead, please, Ryan.
Is the seafloor bottom, is that the reason why there's a slope in the densities?
The slope and the densities?
A slope in the temperature?
No, not really. I mean, you know, if you look here, I mean, the water, that's a good question, actually, if we think about this. So, you know, the water masses are being cut off by the bottom. So the presence of the bottom is not causing the water temperature to increase or decrease. It's just like you had so if you could imagine if there was no bottom here, then these temperatures would keep going down approximately the way they did. But if you just sort of cut off the bottom in some arbitrary fashion, you're going to end up with you know, the temperature at that depth. Like, did I answer that clearly? So
Yeah, I just noticed that there was a relationship with the lines, that the angle of the slope was kind of similar with the ocean floor on the left side. So I thought there might have been a relationship.
yeah, I don't know, hard to prove. I think generally, I mean, there may be some, you know, because you get less mixing, but I think fundamentally, you know, all we're doing is taking the water column structure and then cutting it off at where the bottom was. So, you know, if you drew an arbitrary bottom like that, you know, it would just cut off the lines. So the answer is probably not. Okay, any other questions about the homework?
So is this whole layer still in the mixing zone? This whole graph?
Is this in the mixing zone? No, I don't think this is, no, this is not.
There wasn't evidence of a thermocline, so I was wondering if we got deep enough for it at all, or if this was still, you know, mixing zone area.
Yeah, well, maybe there is. Yeah, this is all mixing zone. This looks pretty, doesn't look uniform at all, does it? And this is actual data, so I copied this from somewhere. So
That's one thing that we were looking for, was like a mixing zone in this, so we
yeah, I
could tell
didn't see
between
it. That's
that
a
and
good
the
point.
thermocline, and it was kind of hard to tell where it would have stopped and ended, because they all seemed to go down gradually from the very top.
Right. So, you know, perhaps when these temperatures were taken, this was at a time when there wasn't active mixing. But you're right, there isn't a lot of evidence of mixing in this upper layer. So that's maybe a poor example in terms of trying to understand that thermocline process. But you know, that's a really good observation. And you know, we'd have to say with these data that there isn't. There's just sort of a gradual decrease, and all of the, you know, they all kind of go down about the same amount. I mean, you could figure the slope of this decrease, and I bet it's the same for all of the casts. You know, it ends up pretty much at the same. So it's, you know, it looks like this is stratified, not mixed. And so you might surmise that, you know, from these data that, you know, this was taken in a period when there was no wind or low winds. And so the water column had the chance to stratify by density, by temperature. But good question. So did you look at that and did you conclude that there wasn't evidence of a thermocline?
We had a long debate about whether we thought there was a thermocline or not. I think we ended up saying that there was one, but it's just because we couldn't find a mixing zone.
Right. Well, I think you, yeah, I think there isn't one. There isn't clear evidence for this, and that was what you meant to say. But it's a good question: is where is the mixing zone? And this is something that happens in you know, in the water. For example, we talk a lot about the dead zone. And the dead zone is, you know, you probably heard about the dead zone. This is this low oxygen region that occurs at the bottom of the ocean in the Gulf of Mexico, offshore Louisiana in particular. And, you know, it can be very harmful to fish and animals that live on the bottom because the oxygen disappears. And the reason the oxygen disappears is because there's a high organic load, and the biological oxygen demand removes a lot of the oxygen down to the point of, where it's hypoxic, it's low levels. And that occurs when the water column is stratified, when there's essentially no mixing, and it occurs in the bottom layers. And then what makes and so that's during the summertime, during periods of low wind, there isn't mixing. And so the dead zone goes away when you get a storm, or when we get into the autumn and winter months, and their regular storm and weather events that mix the water column. So this is a realistic, not an unrealistic scenario for summertime conditions if there was a long, calm period without storms or wind events. Does that make sense? Okay. All right. So that was the homework, and this is something that you're going to be doing every week, different homework. There's going to be a different type of homework assignment this week, and let me go over that, because we've had a chance now, or we're having a chance this week to talk about your milestone 1 submissions. And I met today with the snazzy sea urchins. I think I got the sea slugs confused with the sea urchins, so I apologize for that if there was some confusion there. And so Carrie and I have been looking at the milestone 1 submissions from the different teams. They're basically good, but I can tell looking at this, and Carrie has commented as well, that doing the research is, that's going to be the next stage in doing this. So I wanted to take some time at the beginning of this week to go over research techniques and trying to understand how we do literature surveys, because that's going to be a key part of what you do in the milestone 2 part of the homework of the team project for the semester. So in the, let's see, module for this week, we have a document, scientific literature for the term paper, and I'm going to show you this document. We're going to go over it, and this document is the team homework for the week is assigned out of this document. So your team homework assignment is based on the material in this scientific literature for the term paper. So I want to go over that. I'm going to spend a little time showing you how to use some of the tools, and then we're going to break into breakout groups and give you a chance to practice some of this and to work on that. All right. So I need to go back to my screen here. I need to share. And I want to share. That's me. Okay, can everybody see this Oceanography 4008 scientific literature for the term paper? And I want to view this. Okay. So what makes in your assignment, you're meant to, what I'm trying to introduce you to, most of you have already had some experience with this, but we're going to hopefully improve your overall technique as a part of this course, is that you're going to be writing a team project. You need to have at least 10 sources, 7 of which must be from the scientific literature. I think actually I've increased the numbers to take account for the team resource. But what you need to do is to use the basic format and components of a scientific paper in your presentations. And you need to use citations to your research sources using standard scientific style. You have to incorporate figures and tables that you take from the literature or that you put together on your own, and you have to present them in a proper format. And so what we're going to do here is to give a brief review of how that works, and what is scientific literature and how are these elements expressed. So scientific results generally become official when they've been published in peer-reviewed journals. So if a scientist or a team of scientists wants to publish their results, and publication is absolutely required for science, they submit their manuscript for review to the journal that they want to publish it in. And that manuscript is then reviewed by experts in the subject and the peers of the scientists. And this peer review articles are descriptions of scientific results that are organized and presented according to this general format. And this kind of literature, this kind of result, is the sort of the hallmark, the benchmark, the gold standard of a scientific paper. And so we distinguish scientific literature from popular literature or magazine journalism because of this peer-reviewed process. So if you read an article in the New York Times or an article on, in People magazine, that article is, journalistic standards. They're not meant to publish things that they know aren't true, but there's nothing like the sort of rigorous review that peer review does. So what are the different components? The first component is the title, and that describes the topic of the research and what's going on. But before we get there, we'll see that most scientific papers will have a masthead like this. And so the title page of an article published in a scientific peer-reviewed journal will give the title of the journal. In this case, the journal is called Deep Sea Research. And then it gives you the volume number, the date of publication, and the pages that the article occupies in that volume of the journal. Okay, so when you see this kind of a masthead, that's a pretty good indication that you're looking at a peer-reviewed article. So peer-reviewed articles have titles, and the titles have a different function from literature, from journalism. So if you look at an article in the Washington Post or in People magazine, the title is designed to catch your eye, to be punchy, to have an emotional impact on the reader, to cause the reader to stop and want to read the article because they respond to the way that the title is written. Okay? Well, it's similar for a scientific paper, but it's different in that when you go to review scientific literature, typically you're looking for specific sorts of topics and specific sorts of findings. And so you're not interested in the sensational aspects, but you want to know the content. So the title of this article, and this is an actual article that I've taken from the literature, Evidence of Methane Venting and Geochemistry of Brines on Mud Volcanoes of the Eastern Mediterranean Sea. So that's a kind of a long-winded title, but you notice how very specific it is. Evidence, methane venting, geochemistry, brines, mud volcanoes, Eastern Mediterranean Sea. There's a lot of information packed into that title. Telling you what it's talking about, the specific characteristics of what it's talking about, the kinds of geologic features, the geographic location of the research. So that's a nice descriptive title. And after the title then, there's a list of authors. Very frequently, particularly in the modern world, journal articles are published not by individuals, but by teams, groups that are working together, just like your teams are working together. So this is the list of all of the articles. Now, typically, it's not always this case, but typically the lead author is the person who's responsible for the final writing and editing of the paper, submitting it to the journal for peer review, and then when they have to revise the paper, coordinating the responses of all the different authors. So in this case, we've got Charlot, Donval, Zitter, Roy, Jean-Baptiste, Fouché, Woodside, and then the scientific party. In this case, the Medinaut scientific party, that's describing the whole team. This could be, 10, 11 people in this party, and they're listed as corporate authors in the list of authors. Another convention that you typically would have, so if I write a paper with Kerry O'Reilly and several other authors, because I'm the head of the laboratory where Kerry O'Reilly works, my name would typically go last. And if Kerry was writing the paper, her name would come first. And so when I write papers with students or with postdocs that come out of my lab, even if I am heavily involved in the writing, I tend to put my name last. So that's another little convention. But that varies from lab to lab, from person to person. Okay, so authors, often multiple, and the full contact information is listed here. So this tells you where Jean-Louis Charlot works at the Department of Geosciences in Marine at Ifremer in France. And then we also have the University of Bretagne. These are all French authors. And then here's the Faculty of Earth Sciences at the Free University of Amsterdam in the Netherlands. So this is an international group. Okay. What else have you got here? The keywords, some other things to look for, the abstract. So the abstract is a very brief summary of the research approach and major results. Keywords are terms specifically chosen to help authors, to help readers find their paper, to help search engines to find this individual paper. The introduction reviews the previous work on the topic with this extensive citation of previous literature. Materials and methods describes the samples and observations. Results is the detailed findings of the research. And the general rule is that the results section should say what the authors found, but not discuss what it means, or drawbacks or extensions of what it means. That's what you do in the discussion section. So typically in the discussion, the authors will go back to so in your introduction, you talk about what the previous work on the topic has done with extensive citation of the previous scientific literature, and you explain the purpose of the present observation. Well, when you go to discuss that, you're going to refer back to those original, to those previous literature results, and you're going to talk about how the present findings extend or contradict or modify or add to results that were previously published. And then finally, conclusions. Here you'll make statements of fact that you believe that your research has demonstrated. And so a lot of times you can get a good sense of what an article is about without reading the whole paper. If you read the abstract and then go to the conclusions, you can tell pretty quickly, or you can get a good overview of the what the work has accomplished. And then there's other things. There's acknowledgements. This is very important. So you make statements of fact about what you list other people have contributed to the work, the captain and crew of the research vessel. You mention where the funding came from to support the work and so forth. That's comes in the acknowledgements. And then here's a really important part. This is the references, or sometimes called literature cited. And this is a detailed bibliography of all the research sources that are cited by the authors of the paper. And it has a very exact formal format called the bibliographic style. And that format, the details of that format are specified by each individual journal. And so here's an example from this paper of the first seven references in their final section of bibliography. So here they are: Aaron, Alosi, Atkins, and so forth. And you'll see that each one of these references lists the authors, in this case, last name followed by first initial. And this is the same order that the author list would appear on in the publication. And then the whole list is sorted in alphabetical order. And then there's a date of publication. So the data, if there were articles by two articles by the same author or group of articles, they would be sorted in by the date of publication with the earliest date coming first. Okay? But and so each entry in the bibliography, the references will list the authors, the date of publication, the title of the research paper, the journal that it was published in, the volume of that journal, and then the pages in that volume. Okay, and so that's very specific. And the reason for being so specific is that allows anybody who wants to find out what Aaron Schwartz and Roberts were thinking about radiometric dating of hydrocarbon seeps in the Gulf of Mexico to go to the Journal Geologic Society of the American Bulletin, volume 109, and find this exact publication. Okay. Nowadays, you can do that electronically, and a lot of the search techniques are fully automated, and so it's a lot easier to do. But you know, this basic information is what's required. And in many of the, you know, the convention nowadays also is to include links to that, you know, can send you to the actual article. So sometimes in modern bibliographies, more recent bibliographies, you would actually find links. Okay. So citations and so forth. Okay, now you're required for your paper to come up with figures and tables to present graphic information about the material that you're covering. And these graphics should also have to follow a very specific format. So you'll notice in the paper that, so if we go to the quoted section of the paper, so here's the beginning, where is it? You'll notice that the text refers to a figure, and figure 1. And so figures are graphic elements. They're maps, they're diagrams, they're data graphs, etc. They're always graphics. They have a caption below the graphic that gives the figure number and provides a standalone description of what they show. So this is figure 1 from this paper by Charlou et al. And so here it is. This is the figure number, and then it's figure 1. Sometimes they write out figure, sometimes they just say fig, sometimes it's capitalized. It depends on the journal. But in the caption will always give you the figure number, and then it says what it is. A location map showing the Olympi mud volcano field and the Anaximander Mountains in boxes. So these are the two areas where the research was done. And in the context of the Eastern Mediterranean. So these are some geologic features of the Eastern Mediterranean. So trenches, a deformation front. So this is, you know, giving you some information about the geology and geography of the region where the research was done. Okay? And then, so here I've indicated that this is figure 1. This is an example of the paper from with the original citation. And so in the original figure here, what you notice is that the source of this map is listed because it was previously published. Well, most of the figures that you're going to use in your research are going to be previously published. So when you go to write your figure captions, you're going to have to include a citation to that, to where you got the figure. So in this case, they're saying that this came from this publication, Shipboard Scientific Parties 2000. So that would be a reference to where this data came from. Okay. Now, tables are also an important part of a scientific paper, and they can occur anywhere in the body of the text. But a table, unlike a figure, contains no graphic elements. There are some exceptions to that, but the standard definition is that there are no graphic elements, just text and numbers. And the text and numbers are arranged in rows and columns. So this is table 1 from that figure. And what this table is telling us is the location and depth of vertical stations sampled during the ascent of Nautile. Nautile is a submarine at the end of these dives. Okay, and then so here's the columns and rows of figures and text. And so this here's the station name. So PL03, PL04, PL08, the name of the site, and the latitude and longitude, and then the depth in meters. Okay, so and so this is how tables are organized. And a table caption comes at the top of the element, not at the bottom. So that's another way that you can distinguish tables from figures. And this really seems to be a struggle for students, I've noticed over the years, is getting tables and figures confused. Now we don't, mark off, nobody flunks the course for getting that wrong, but this is something that you should try to incorporate to be able to comply with the formalism of a scientific paper. Okay. All right. So that was a review of a particular paper, and what I want you to do in your team homework assignment is you should go to the Science Direct site and select Deep Sea Research Oceanographic Papers, and then search for this particular paper. And this will give you a link to the full PDF version of the Charleau paper we've been looking for. And then I want you to answer the question, what are the keywords listed by the authors of the paper? So one way to access this paper would be through ScienceDirect.com. We're going to look at another method in a little bit here. And so, one of the problems that's arisen recently is that the FSU library no longer pays subscriptions for Elsevier and some of the major scientific publishers. And so it can be a little more difficult than it used to be to access online articles. And so I'm going to try to walk you through some ways that you can always be able to access papers. So you'll read this and you'll see this. Okay. So that's that's an overview. These are questions that you have to answer about this Charleau paper. But now I want to spend some time looking at the a really important tool, and probably the only research tool that you actually need, which is the Web of Science. And this is a database which is available through the FSU library homepage at this link, and this link is embedded here. To access the Web of Science, you need to be logged into FSU Library Services. But if you're once in the library services, then you get full access to that database, plus all the embedded tools in there. So I've got a bunch of examples in the document here, but instead of looking at that, what I wanted to do now was to go to the actual Web of Science, and we'll go through that, and I'll show you some of the search tools that you can use there. So I need to stop sharing this screen. Share this screen. And I'm going to open a new page, and I'm going to go to Web of Science. Okay, here I am in the Web of Science. And so this is what you'd see. Just a little bigger.
We're not seeing that.
Can you share your screen?
Okay, sorry, I thought I had. Thanks for letting me know. Okay, you see it now?
Yes.
Okay, good, thanks. All right, so here's the Web of Science, and this is a fantastic tool. I mean, I can't tell you how much this helps in doing the task of doing literature surveys and research in preparatory to research papers or actually writing an actual paper. So what the Web of Science does, it's embedded in the title. It's a web of information related by scientific citation, and it's all about science. And so there are search terms, probably familiar with this, and you'll see that there's a menu of items that you can search on. And so we're going to start by searching on author, and then you can add rows. So I'm going to add another row, and I'm going to add topics. Okay. But over here, there's a screen that lets you put in Boolean identifiers or Boolean links. So you can say and, or not. So I'm going to search for an author and a topic. But you could also add another field, and you could specify, you could narrow your search by specifying years, last 5 years, last 4 weeks, custom year range. These are all ways of narrowing your search, being more specific about it. Okay, so for this example, and this is what's in the thing, I'm going to ask you to search for an author, and I'm going to pick an author, Charles Fisher. Charles Fisher is a colleague of mine, somebody I've worked with, and he's done a lot of work on corals. So I'm going to write in Fisher C with an asterisk, and that's how you do your, you enter authors in. So the last name, the first initial of the first name, followed by an asterisk. So that's going to find all of the people with Fisher. All right, well, let's look what happens. Let's look and see what happens if I just look for Fisher C in the literature without any other qualifiers. Well, I have 487 pages of results, and there are 10 results per page. So obviously, I've got 4,000 different search results for authors named Fisher. 4,869 to be exact. So that's way too many to search through, particularly if you're getting things that are not related to corals at all. Changes in sexuality, education, teacher training since the release of the Australian curriculum, that's clearly not about corals. So we want to go back and refine our search term. All right, so I'm going to add here corals. And let's see what happens when I add this restrictor. Okay, well, instead of having 4,000 results, I've got 22 results. Okay, so here are the results here. And then, so these are the actual articles written by Fisher. Now, you'll notice that Fisher's name does not show up in all these entries, and that's because he's probably a secondary author. But here the search terms are illustrated. So here's Fisher Charles, here's corals, and so this is showing you how the index terms are achieved. Now, you can sort these results by a variety of different methods. And so you can see sort by up here. You can sort by date. In this case, the date is sorted from the most recent first, the number of times cited, the usage count, and there's other ways that you can search. First author, source title, conference title, and so forth. Different ways of organizing your search. So let's do this by, all right, so that's one thing you can do. All right, and you'll see that this is the most recent set of papers. And so this is the most recent paper that to be released. If we click on this, that brings up the full author list and all of the full title. Okay, so in this author list, we can see that there are bunches of different authors, and Charles Fisher looks like the 8th author or something like that. And there's even more authors. So there's this really, really long list of authors, and Charles Fisher is one of those authors. And so that's kind of typical of many scientific papers that you'll find. So if somebody is writing about characterization of deep sea benthic invertebrate megafauna of the Galapagos Islands, well, the corals are just a subset of that. So there are many other authors that have contributed to this report. What else do we see in this this literature here. We see an abstract, and so this abstract here is giving you the bare bones outline of what the paper found. Okay, so the deep sea represents the Galapagos Islands, one of the most pristine locations, and so this is telling you what's found here, and then here are the keywords, and you can see that the keywords included corals. So that's how this paper shows up in our research results, because it's by this author, Fisher C, and it contains this term, corals, not in the title. I'm not sure if it's in the abstract or not, but here it is in the keywords. And so those are the terms that the search engine went through, crunched through to pull back this list. Okay. You see some other things here. The number of times cited. Well, this has never been cited, 0 times cited. And the number of cited references. Well, the number of cited references, that is the bibliography of all of the papers that were cited in this article. And I can click on this and view that bibliography right in the engine here. So here they all are. Here are all the articles in the thing here. Okay. So when you do this, you see that there are many different articles, and there's a lot more information here. And you can analyze these results. And so ecological variables for developing a deep ocean monitoring and conservation strategy. This has been cited 19 times, so it's a pretty important paper. You have some other things. You can find it at FSU. You can get download a free version of this. You can view the abstract. You can do all of that. Okay. Well, let's back up a little bit and go and look here. So one of the things that you're going to have to do when you've got a whole bunch of results is decide which one is important, particularly if you're doing sort of fundamental research and trying to understand, a different problem or topic. And one way to evaluate papers is by the number of times that they're cited. Okay, so in our exploration of Charles Fisher and his results, we've sorted by the most recent date. So this article, Characterization of Deep Sea Benthic Invertebrate Megafauna of the Galapagos Islands, has not been published. It was only published in August of last year. So there hasn't been time, it hasn't been out in the literature for long enough to anybody else to cite it. So if instead we sort this list of coral publications by Charles Fisher by time cited, we can see that some of the papers he's written has been cited quite a lot. So here is a very widely cited paper, The Impact of the Deepwater Horizon Oil Spill on a Deep Water Coral Community in the Gulf of Mexico. This has been cited 213 times. So this is a very influential paper. 213 citations is exceptionally high for a particular paper. And so this paper proved valuable to many other authors. The next most highly cited paper by Charles Fisher, including Charles Fisher as an author, is Coral Communities of the Deep Gulf of Mexico. The first author here was Eric Cordes, who happens to be Charles Fisher's former graduate student. Okay, and then we get down to Footprint of Deepwater Horizon Blowout, Impact on Deepwater Corals, cited 79 times, and so forth. Fewer and fewer citations. Okay, so those are some tools that you have for evaluating these things. Okay, let's see. Let me go back to search and we'll play around a little bit more. So I'm going to take out this, remove this, and I'm going to make this topics. And I'm going to say deep sea. Let me do something else. Let me do oil spills. Okay, so I'm going to put out a topic there, oil spills. And this comes up because I just had a conference with the snazzy sea urchins this morning, and we were talking about their research on oil spills. So we just did this search. So if we do this search, we come back with 16,997 papers that describe oil spills. Wow, that's, you could spend years going through this literature. People do. So how do you want to refine this search? Well, you could do it by time cited, but you can see that there's a lot of stuff in here, and some of this stuff is just sort of, outside of your field. So let's go over here and figure out some ways to refine these results. Well, one way to refine these is by looking at document types. So there's articles, so there's 12,000 articles, and these are just sort of any old articles. There's 3,000 papers from conferences. There are 432 book chapters, editorial material, and then there's this review. So if we check on this review topic here and refine our search, we're going to go from 16,900 findings, or 17,000 findings, down to only 630. Click on that. There we are, 630. Now, within this thing here, you have a bunch of different choices. So there's different choices that you can make here. Environmental sciences, marine freshwater biology, more options and values. So there's a whole series of things that you could choose to categorize. And so you could choose any of these topic areas. Back. All right. Another way to do it would be to look for highly cited papers. So let's do that. So we've got our review articles, and we're looking for highly cited. So that's 23. Okay. So we've gone from 16,000 down to 23, and we still want to refine this a little bit more. So we can go from, we're not interested in the physical chemistry, we're not interested in material science, multidisciplinary. We just want to focus on the environmental sciences. If we do that, we end up with 10 review articles. So state-of-the-art satellite and airborne marine remote sensing by Ira Leifert, cited 249 times. Review of oil sensing remote spill, 219 times. Environmental effects of Deepwater Horizon oil spill. Okay, so you can see how you can get to these different results. Okay, all right, so that's one thing that you can do in Web of Science. Another thing that you can do is to put together your bibliography. So let's suppose I've looked at this and I'm really interested in remote sensing and the, okay, so I've selected these 3 articles. And I think these are ones that I really want to look at in more detail. So I can mark these and I can add those to a marked list. So now I have 4 articles in my marked list. If I go to this marked list, here are these articles. Okay. And any of these you could find at, so if we want to look at state-of-the-art satellite and airborne sensing, published in 2012, if I click on this, that's going to take me right to this paper. And then here you have that paper. So that's something that you could do. And that's a skill that I want to instruct you on. Okay. So I've covered a bunch of stuff here. And let me go back to the, all right. So once you did that and you wanted to, so you've got your list of things here, you can preserve this. You can make a bibliography and you can export this. Now there's a couple of different, and so you can save this marked list of articles that you're interested in as a separate file. There's a couple of ways to do this. Now, right now, these are the fields, information that's going to be carried out. So we can export this. We can export it to print format. So if I put this into print, I get all this information about those papers. All right. Now this isn't quite what I wanted to see, so let me go back, and I want to have the abstract. I don't want to have the times. I don't need this. I don't need this. I don't need conference information. I don't need this. So I can refine that and print it out. Okay, so here they are with the abstracts in this. So you can see that if you've done a bunch of research and you wanted to save your research results, you know, you could build up a preliminary set of findings here very quickly using this Web of Science. But wait, there's more. So let's close this, go back. So I've been exporting to print, but we have choices. We could also export, oops, I want to do that. I wanted to change the results. So these are giving you different ways of exporting these things. And so these things like RefWorks, Incites, and EndNote, these are all ways of exporting your findings to a bibliographic software that will let you easily embed these things. And so EndNote Online, let's see if it works. No, this is not finding that. But you can set up EndNote Online, and you can do it online, and you can also do it in desktop. So I can export to EndNote Desktop, and then I could open up that paper in EndNote and be able to use other tools. Okay, so I think we're just about out of time here, but I wanted to leave a little time for group work and questions. So stop sharing. Does everybody follow along with what I've presented here about ways of doing literature surveys and using different tools, what a scientific paper is like, you know, the specific structure of a scientific paper, the format of a bibliography. So those are all things that you're going to need to, you know, probably you're already familiar with these things, but we're trying to make sure that everybody's on the same page and focused on presenting their research findings in the same way. So can I answer any questions about anything that I presented today? Questions? I love questions, so make me happy. Ask me a question. Yes, Joseph Helton, I see you have your hand raised. Nope.
Hi, so is any format fine? You want us to use oceanography format, or is APA fine as long as we're consistent about it?
I will accept any format. I think that I say there in the homework assignment, I want you to do it with Deep Sea Research, the format by Deep Sea Research. But you know, as long as you pick one consistent format and use that throughout, that's okay. I'm not going to try to tie you down to one for it. But you're looking for journal formats. So each journal has its own format, and you want to copy that format when you prepare your own bibliography and when you do your own in-text citations.
Okay, thank you.
Okay. Other questions? All right. So I'll tell you what I'm going to. Yes, go ahead, Joshua.
I was wondering if the FSU libraries are still like the computers are still like open for use. Is that it? Like really still like, and are the hours changed? Does anybody know?
You know, I'm not sure about the library. I think they, you know, I think you have to pretty well access most of it online. You know, the computers, you can log into, if you go to the library homepage, you can log in remotely. And then Sage says that the computers are open for use. All right, so thanks for that, Sage. And the hours are 8 to 11. All right, group wisdom. Okay, And so what we'll do, I just have a bit more I want to cover about ocean chemistry. I'll get through a bunch of that as much as I can next week, and we'll break out into breakout groups. We don't have quite enough time today. I mean, I can open the breakout rooms if you'd like. How many folks would like to stay and work with their teams in the breakout rooms, and stay after class a little bit to get oriented around this assignment? Could I get a show of hands, or because I can open the breakout rooms and you could join and have a few minutes to talk about completing this homework assignment. Looks like just one person is interested in breakout rooms. All right, well, in that case, I will not open the breakout rooms today, but I'll encourage you to figure out a way to get together, because you'll need to go over that team assignment, and there's a set of questions in there. Let's see. No, that's not what I wanted to show. All right, if you look at the very end, I'm asking you to do some research on publications that I have written. So for your homework, you're going to be searching for my name, MacDonald I, and then you're going to be using the search term chemosynthetic. And then you're going to export a marked list of publications that meet the following criteria. I want you to know the total number of results, the most recent paper, the oldest paper, the most cited paper, and then I want you to find one of my papers that's been cited 131 times. I want you to find a copy of that paper and describe what you see in figure 4 of that paper. So that's the homework assignment, or the rest of the homework assignment for the teamwork. And so you can do that. Probably be easier if you work together to do that. Okay. All right. Well, that's what I have for today. If there are no more questions, I'll say goodbye, and we'll see you on Thursday. So, any questions? I'll hang around a little bit longer if anybody wants to meet.
Thank you.
Okay, thank you. Okay, bye now.